So let's talk about optimizing model efficiency. So the problem, the accuracy is not enough. So far in training neural networks, we usually focus on accuracy. Example, model, let's say they have CNNA and the accuracy of it is 92% and the CNNB and its accuracy of it is 95%. Normally, we will choose CNNB, but in real world deployment, accuracy is not the only factor. Other important metrics are model size or memory usage, inference time or speed of prediction, power of consumption, latency, or throughput. Example environment like GPU server, main concern is accuracy, smartphone, memory plus speed, drone is power plus speed, smartwatch is extreme small models. A huge model may be accurate, but unusable on small devices. Next is trade-off in deep learning. Usually improving one metric hurts another. Example model is small CNN. Its accuracy is 90%, size is 10 um, memory bytes, and inference time is 5 milliseconds. And let's say the model is ResNet 34, and accuracy of it is 94%, and the size is 90 megabytes, and the inference time is 20 milliseconds. ResNet is more accurate, but it's slower, much bigger, more power usage. So the best model depends on the situation. Next is three metrics used in the lab. The course compares models using three metrics. One is accuracy, as you're already familiar. Accuracy is equivalent to correct predictions divided by total samples. Next is model size, how much memory the model occupies. Example, in the model CNN, size 12 megabytes, ResNet 34 is 83 megabytes. Next is inference time, how long the model takes to make a prediction. Example, model CNN, inference time is 5 milliseconds, ResNet 34 is 18 milliseconds. For real-time systems, this is extremely important. Example application is self-driving cars, um, live video detection, robotics. How PyTorch calculates model size. The function is modeled with parameters, returns all trainable parameters like weights, biases, and each parameter tensor has parameter and element, number of values. Example is 1000 weights. Each value also has a size in bytes. Parameter element size for float 32, each element is equivalent to 4 bytes. So memory usage equivalent to memory is equivalent to number of elements by bytes per element. So example, 1 million parameters times 4 bytes. So we could have 4 million bytes. Then convert to memory bytes. So bytes is equivalent to 1 byte is equivalent to 1024 to the second power. So the 4 million bytes equivalent to 10 to the 24 power is 3.81 megabytes. What is buffers? PyTorch models also contain buffers. Buffers are tensors not trained, like batch norm running mean, batch norm running variance, fixed constants. They are still needed during inference, so they also count in the model size. So the total size is model size equivalent to parameter size plus buffer size. Next is measuring inference time. Inference time means how long the model takes to make a prediction. Steps in the lab. Step 1 is set model evaluation mode, model.eval. Step 2 is send input to device, input to device. Step 3 is warm up, run the model several times before measuring. Why? First runs are slower because of GPU initialization, memory allocation, PyTorch stage initialization, so warm up stabilizes timing. Step 4 is measure time. Run inference multiple times, example 104 passes. Then compute average. The average inference time is total time or iterations. Convert the milliseconds. 1 second equal to 1 milliseconds, right? So next is comparing models. Now we evaluate models with three metrics like um, accuracy, size, and inference. Like if we have optimized CNN 93% accuracy and its size is 12 megabytes and um, inference 5 milliseconds and rested is 34 and accuracy is 91% and size is 83 megabytes and inference is 18 milliseconds. In this example, CNN more accurate, CNN is smaller, and CNN is faster. But in real life, results are often mixed. So let's say if we have model A, 95% and size is 100 megabytes and speed is 20 milliseconds, and model B is 93%, um, 15 megabytes, and speed is 6 milliseconds. So which one is better? It depends. Two strategies help to decide. Strategy 1. Constraint-based selection. Use when strict limits exist. Example deployment, the smartphone can only handle um, um, less than 20 megabytes and inference time is 10 milliseconds. So filter models remove model that break constraints. So is 100 MB, is it model A is valid? Its size is 100 MB and time is 20 seconds, 20 milliseconds, and is that does not pass in the constraints. So it's not valid because um, here in the constraints we said that the model size should not exceed in 20 MB and should not exceed in 10 milliseconds. Model A does not achieve that. So step 2, if no model remains, constraints are too strict. Step 3, among remaining models, pick highest accuracy. Strategy 2, weighted scoring. Use when requirements are flexible. Instead of hard limits, assign important weights. Example weights is accuracy 50%, um, model size is 20%, inference time is 30%. One normalization is needed. Metrics have different scales like this metric accuracy, the scale of 0 to 100, size is MB, time is milliseconds. Without normalization, large numbers dominate. Example, size 80, accuracy is 90. Size will influence the score more. Next is min-max normalization. Convert values 0 to 1 scale for metrics where higher is better. Or accuracy. So normalize x minus mean divided max minus mean. So results model with lowest accuracy is normalized accuracy is 0, highest accuracy is 1. For metrics where lower is better, size and time, we flip the score. So normalize 1 minus x minus mean divided by max minus mean. So the metric, the smallest model is, its best value is 1, fastest model is 1. Next is weighted score. Final score is given weight 1 multiplied by accuracy plus weight 2 multiplied by size and weight 3 time. So score is given 0.5 times accuracy plus 0.2 times size, 0.3 times time. Compute this for every model. The model with highest score wins. Next, visualization. Models can also be plotted. Scatter plot, x-axis is inference time, y-axis is accuracy. That size is model size. This helps visually compare trade-off. So the key takeaway here is modern deep learning engineers optimize three things: accuracy, model size, inference time. So accuracy, the goal is to maximize. The model size should be minimized. Inference time should be minimized. Choosing models is about balancing trade-off, not just maximizing accuracy. So the final concept of learning has two phases. Phase 1 is research, next is deployment. Research is maximize accuracy. Deployment balance accuracy plus efficiency. So production AI always care about memory, speed, cost, power.